All right. Hello, everyone. I am Adrienne Tacke. I'm based in Las Vegas. And if I'm unusually chipper, it's because this is the first time a conference like this has been in favor of my time zone. So I'm very happy that it's the normal waking hours for me here. It's around 3 p.m. for me. Today, I'd like to talk to you about NoSQL databases. Specifically, I'm hoping to possibly reshift your mindset and maybe even get you to say yes to NoSQL databases. So let's get to it. So as relational developers or developers who are used to working with relational databases are probably your bread and butter. They were mine. They were the first data model and type of database that I worked with when I started out as a software developer. And that's kind of just what we used, right? We didn't really have a need for anything else, or we probably didn't learn anything else. And so along with that, all the other parts of it kind of became second nature. SQL is your jam, joins were necessary, data is relational. That's why they're called relational databases. And for the most part, they work, kind of, but they worked. So when this new kid around the block came in called NoSQL, they're probably just like me, like, what is it? Why would I need this? What exactly is NoSQL? And to that, I say you're completely justified. I mean, it's been used in so many different ways. It's been interchanged in different ways. We call it NoSQL, non-SQL, or non-SQL, however you like to say it, non-relational SQL, not only SQL. So with all of these different definitions and variations and mutations of what we assume NoSQL is, it's not really hard to see why a lot of people are not distinct and clear about what is a definitive NoSQL database. And so, but this is not a problem because there are different permutations of it. So keeping this in mind, I like to think of it this way, at least in contrast to what relational developers think of. And so NoSQL is basically a different way of storing and modeling data than the regular form that we are used to. Now, keep in mind, these databases, the notion of NoSQL databases, they've actually already existed for quite some time. In fact, they already were around in the 1960s, but it did not gain popularity and surge into tech buzzword land until about the late 2000s, when costs of storage have dramatically increased. And that makes more sense because, as we'll see in a bit, NoSQL databases have some characteristics that make it more pragmatic for storage to cost way less than what it did before. So if not tabular data, then how do we model it? What do? We're used to our nice structured tables and joins and foreign keys. How else would we model this kind of data? Well, there are four different ways, four common ways that you would find that are related to NoSQL and NoSQL data models in particular. So the first is the document store. So this is where you can store data in hierarchical ways, and they're stored within JSON-based documents. I think I work for one that you may know. It's called MongoDB, but there are others. A second form of a data model for NoSQL is the key value store. So this one, at least when I first started learning about all the different models, was a little bit more self-explanatory. They're literal keys and values, and you would use these keys to quickly query any of the data that you may need. And it's so fast because you would probably hash those keys to be able to get it quickly. So think your Redises, your RocksDB, your Apache Ignites. Next, there's the wide column store. They might be interchanged with columnar stores. I always say that incorrectly. I always get self-conscious when I say it because I think I'm saying it wrong. But I'm going to say wide column store. And this is where related data is stored as a set of nested key value pairs within a single column. So for me, when I first read that and even saw some of the diagrams, it didn't really make sense to me. But what did make sense to me is if you imagine, let's say you had a customer column, and within that column, you actually had two things like name or address, some sort of related data that you would want to query together. Now you might have another column with completely different data, but is related to that person or that row ID. And let's say you have a product column that could include the item and the price. So in the wide column strategy, you would then be able to query either via user ID or something which would equate to the row of that table, but be able to quickly get the actual group of data that you need in this wide column store. So these are your ScyllaDBs and your Cassandras. And finally, there are the graph store models. So this is where we store data in nodes and edges. So nodes store the entities, the nouns, the people, the places, the things of the data that we're capturing. And the edges store the relationships, or I like to call them the verbs of what is related among these things, these entities. So these are your Neo4j's and your Janus graph. So keeping in mind that these are a different way of modeling data and that they have a different approach to storing data, naturally, the next question that usually comes to mind when we start discussing this is, all right, so are NoSQL databases better than relational databases? Well, technically, I'm paid to say yes. But the real answer, of course, is it depends. The lovely answer that is right almost all of the time. It depends. And so in order to truly understand why the differences matter and how we can use some of the things or use the differences in our decision making, we need to get some dependencies into this presentation. In fact, we need to import some dependencies into this presentation about some of the fundamentals. And I know if you've heard this before, it might just be a quick refresher, but I promise you that laying these fundamentals down and understanding them will help in the later part of this presentation, and hopefully in the later course when you are making a decision on whether or not to choose a NoSQL database for your system. So those three dependencies are going to be the cap theorem, acid, and base. And before anyone says anything, before you start typing in the chat in Slack and saying, oh, this has been outdated, this has been debated. Yes, I have read those articles. I've read Martin Kleppmann's response to cap theorem. I understand. But the point I want to make here is the fundamentals still stand, and they still give us a very good framework of at least asking us or forcing us to ask the questions with ourselves and with our team on whether or not we need some of these properties and things when we are deciding on a technology to choose. So keeping that in mind, we'll go through them. So cap theorem, also known as Brewer's theorem, based on the computer scientist Eric Brewer, who has projected this out into the world. And so he states, in a distributed system, it is impossible to have more than two of the following three properties. That's consistency, availability, and partition tolerance. CAP, right? Because we just need more acronyms in tech. So quickly, what are those? Because even these are contested in what they actually mean. And at least for the context of this presentation, I'd like to tell you what I see them as, or what I feel they should be. Consistency states that a read from any node is guaranteed to return the most recent state. So what does that exactly mean? Let's say I have a cluster and I have 4 nodes. And in these 4 nodes, these are 4 computers, whatever, I'll call them nodes just to be more generic. We can read and write to this cluster. And right now, the current state of my cluster is it has hey there in all 4 of the nodes. That's the state, that's the value of all 4 nodes. Now, let's say I want to update the value to kumusta instead of hey there, because I figured if for those who already know cap theorem, hey, maybe you'll learn something new too. So kumusta is hey there or hello in Tagalog. And when we send this call, when we send this operation to my cluster, what will happen is, as expected, it will probably update the first node that it reaches that accepts the call. But in an inconsistent system, what could happen is that before replication is finished, we might actually acknowledge to the client that, hey, I'm done, I've written. And this is inconsistent because what if right after that we decided we wanted to read something? And this is done before the replication has finished. And let's say that this read call was sent to node 3. Well, you can see the problem. We're going to get the value hey there instead of kumusta. So this is where we say it's an inconsistent system because we're receiving stale data. We're not getting the guarantee of the kumusta on all of the nodes that we are expecting. Contrast that to a consistent system, what would probably happen is we wouldn't acknowledge to the client that we were done until it has been fully confirmed that everything has been replicated to the majority of the nodes, to all of the nodes, depending on some really granular things like write safety and write preferences and MongoDB and all the other options. But in a consistent system, we would be guaranteed that no matter which call is made and no matter which node accepts it, we are going to get the same data. So that's consistency. A read from any node is guaranteed to return the most recent state. Next is availability. So availability in the CAP theorem states that every request received by a non-failing node will return a response, meaning no errors or timeouts either. So let's go back to our cluster. Same 4 nodes, same values, all hey there. Now, in an available system, if we made a call, we would be able to still receive a response, despite having, say, 2 nodes go offline, just like it did in my cluster. An available system would be able to write kumusta, and it will reconcile the replication of this in the back end, but to the client, to the front end, it's always available. So that's where we get the problem of it could still be sending us stale data because it's always available. And you'll see that with if we try to say, read this now, and that read call went to, let's say, the 3rd node, we would still get hey there. So there's that possibility of stale data in this particular system. But being available just means that even if there are nodes down in the cluster, we are able to still have a functioning system. It doesn't break because 2 nodes are down. So availability, every request received by a non-failing node is going to get a response. And lastly, partition tolerance. So despite network partitions, aka when connections are severed between nodes, they can't communicate to each other, again, the system should still function. So back to our cluster. We have 4 nodes. Hey there is all there. Everything's fine and dandy, right? Now, let's say that some communication breaks between node 1 and node 4. There's no way for them to talk to each other. And, if this needed to write or replicate something, it's not able to do so because the communication has been severed. Well, a partition tolerant system says that even if this state exists right now, even if node 1 and node 4 can't talk to each other, we're still going to get a response. The system is still going to be functional for the user. So partition tolerance, despite network disconnectivity or severed connections between nodes, system should still function. So CAP's theorem says that we should only choose between these 2, or we can only have 2 out of the 3. We can only have 2 out of 3 of consistency, availability, and partition tolerance. And again, we can argue that that is kind of being challenged right now with Spanner, but again, we'll save that for later. So this means that this area right here in the middle, that we can't possibly have all 3, at least with a fundamental understanding that most of us have known for a while. So with this in mind, this means that there are several combinations left for us to deliberate on when we choose on how to architect our system. But do we really? Because of the nature of distributed systems, we really only have to choose between 2 options, or we are only left with one or the other choice that we need to deliberate on because one has kind of already been chosen for us. So One of the logical fallacies of distributed computing is that the network is reliable. You'll even see here it's listed as on the official Wikipedia of fallacies of distributed computing. It's number 1 on there, that the number 1 fallacy is the network is reliable. Networks are not reliable. They go down many times. It's unexpected. I know many of you have probably encountered some sort of issue with a video call. Networks are unreliable. And so because we understand that network failures will occur, and they will at some point happen to our system, it's a given. We must tolerate partitions in a distributed system. So this is why I say partition tolerance is an automatic choice. It's not left to us. If we're going to work with distributed systems, it is chosen by default for us. So now we're left with 2 options, right? Do we choose partition tolerant consistent systems, or do we choose partition tolerant available systems? In other words, which one are we willing to sacrifice, consistency or availability? In partition tolerant consistent systems, obviously we're sacrificing availability. But here, if we choose a system like this or build a system like this, when consistency cannot be ensured, we will probably get errors or timeouts. And in this kind of system, that should be acceptable because we care more about the data integrity rather than the availability of our system. So if consistency is crucial to the user experience, then these are some factors that you would consider and maybe leaning towards a partition tolerant consistent system. So you have to decide, are errors okay to show to the client or are they not? Is consistency literally the thing that matters most in this application or is it not? And that's why the example of financial transactions or financial applications kind of uses this, because we all want to make sure our money is in our bank accounts and it's the right amount. Now, if we go the other direction, we say consistency is not really too important. Availability is way more important in our application, in our system. Now, we may not get errors or timeouts, but the problem here now is that the data you receive could be outdated. So even though it's always on, always available to the user, what's more important in these systems is that data accumulation, the amount of processing and writes that you're able to do on this system, is more important than data integrity. So in these cases, it's where eventual consistency is acceptable. It's where everything does not have to be the same mutual state, correct at the same time. It's if this is at some later point, it gets to the right state, that's okay. And so these are some of the things that you have to consider when you are deciding between these kinds of trade-offs. And one last thing to note about this is that, so when we learned about this, or maybe if you're hearing about this for the first time, it might seem like these are these very binary design decisions, right? You have to sacrifice full availability. You have to sacrifice full consistency, and that's absolutely not the case. In fact, Eric Brewer himself came back, some years later and was like, it's not really that rigid. What's happening more and more nowadays is it's more like a balancing act. What are the trade-offs that you are willing to make? What are the trade-offs that your system can make and are acceptable? That's what we are trying to find now. But the fundamentals of this still stand, where it allows us to ask those questions to get to those answers, to see what is worth sacrificing and what percentage or level of consistency and availability we want to balance. So the funniest thing about this is that while I was, finishing up my slides on this and talking about consistency and availability and making sure all my animations are sparkly smooth, at around 8:35 p.m. last night, I used Slides.com to create my slides. I used to use Reveal.js, which is the open source project that this is based on, but it got way too tedious. So I gave in and got Slides.com. And I got this. And this is the last thing I wanted to see. At this point, I was telling myself, you know what, Slides.com, I'd rather you be available right now than consistent. But Alas, we're still here. I was still able to make my changes, and I only lost maybe a couple objects. So it's a win for me. Great. So now we've laid the foundation for CAP theorem. We understand the trade-offs that we have to make between consistency and availability in a system, where we are now assuming that partition tolerance is default. It's by nature, it's a distributed system that is chosen for us. It has to be that way. The next thing that we need to understand is the ACID properties versus base properties. So you've seen these acronyms before, maybe, or if you've ever done any kind of research on databases, you'll see this somewhere. And what I want to make very clear is that these are not one-to-one direct comparisons of the properties of each other. They are more like a set of guidelines that you, again, have to decide if it is right for your system or not. So the consistency model in ACID, very quickly. A, atomic. All operations in a transaction succeed. Otherwise, roll back the entire operation. Either it all happens or it doesn't at all. And then for C, consistent, meaning upon the completed transaction, the database is structurally sound, meaning that the data should be in a consistent state both before and after a transaction. I is isolated. That means if you have concurrently running transactions, they shouldn't affect each other. They shouldn't contend with one another. And the D stands for durable. So upon a completed transaction, despite any failures, the results that happen should be permanent. So meaning if there are any hardware or software failures, any changes that have been committed to the database should still remain. So as you can kind of sense, or if you've worked with this, or you know you needed this in your systems, you'll know that these are very rigid. They're almost like a pessimistic model, a pessimistic consistency model that you need to guarantee. And these are very much directly related to the transactions themselves in databases. So that's one thing to keep in mind, because these ACID guarantees kind of imply, not always, but imply that write safety is more important for you. Now, if we compare the base properties, base, BA, basic availability, means the database appears to work mostly. It's mostly available. It's mostly there. The S stands for soft state, which means that the database state, you need to be aware that it could change over time and due to eventual consistency, and also if there are no inputs that are happening at the moment. And E itself is eventual consistency. So the database will be consistent at some later point. So knowing all of this, you can already see that these are much looser properties. They're not as rigid as ACID. And in fact, a lot of research has shown that NoSQL databases kind of naturally fall more into the base properties because they have those more lax guidelines than ACID. But these are, again, things that you need to understand and be aware of, because if you can get your team and yourself to acknowledge and answer these questions of what your system actually needs, you'll actually be better off in the long run when we finally get to the point of choosing a NoSQL technology, if you ever get to that point, and if it makes sense for you. So all make sense very, very soon. So we have spoken about CAP theorem, we've spoken about ACID, we've spoken about base. So now we can finally get into the what I call the 3-step guide of ditching relational databases. So number one, now that we have the fundamentals covered, the first thing that we need to discuss is NoSQL actually the way to go? In the very end, is this even this is the first question you should ask and start with, because this will not only cut you off short, this will also lead the way into whether or not NoSQL databases should be the way to go. And how do you do that? Well, there are more things that you have to consider. But for this first step, what you really need to take a look at is your data, specifically 4 characteristics of your data and how they describe your data. So when you're determining whether or not NoSQL is the way to go, you want to look at your data volume, your data velocity, your data variety, and your data valence. And as a general rule, very quick TLDR, if you have large data volume, if you have high data velocity, if you have volatility or high volatility, varied types of varieties of data, and if you have a high data valence, then generally NoSQL is probably the way to go for you. So that's like general rule, although there could definitely be some exceptions. But for the most part, if you fall along that spectrum, NoSQL is probably a good bet. So what do these mean exactly? There's all these words, and I like to structure things and use alliteration here with all the same letters. But what does this actually mean? So to start, data volume, meaning the size of your stored data. How large is your stored data? And if you look at the data sets that we have now, large data sets are becoming even larger. They are so large, in fact, that they are almost becoming too unwieldy when we store them in a traditional relational database model. So what that means is whenever we have to query something, whenever we have to query against a really large volume of data, if it's in a relational model and if it has been modeled the way we are used to, which means there's going to be lots of tables, there's going to be a high number of joins, then it's going to be very, very, very slow. So it's not a fault of relational databases themselves, but rather the data model. So in this particular case, I say if your volume is large, NoSQL is probably a better option than a relational data model because they are much better at handling today's larger data sets. They've been built to improve upon that fact. Next is data velocity. And what I mean by this is the rate at which your data changes over time. So there's two parts to this. And the first one is if you have high write loads, meaning if the rate at which your actual data points change, meaning how many edits you have and how many times you have to write to the database, if that is high, and if the actual data structure, your data model, your schemas change constantly over time, if both of those are high, then again, it's another consideration leaning towards NoSQL being the better option for you. Think about it. So if you pair the first characteristic, which is having a large volume of data, you pair that high volume with really constant high write loads, you're basically pushing whatever database that you're using to deal with this amount of surging database activity. You're going to be peaking all the time. And then when you talk about the data structure, you have the changes that occur over time. And this can happen for many reasons. Businesses move fast, organizations acquire data acquisition is experimental. You realize that the model you had was not correct, or maybe you have new things that you need to capture. And again, if you've worked with this in a relational model, you know the pain of migrating a data model, especially if it's only just adding one extra field into the table. With all of these, you have to consider that if you have these characteristics, if you have large volumes of data that you're dealing with, if your velocity is high, meaning you know you have a lot of writes and you know that your data model is changing constantly, you almost require a database that is optimized for the high write loads and for the flexible data models. Those are two things that a relational database is not usually prepared to handle, and even more so if they're not properly tuned. So it's not saying they're absolutely not possible. It's just saying NoSQL databases have been built with this in mind. And so for that, if you do have high velocity, then NoSQL is probably a better way to go. Thirdly, data variety. If you have high data variety, meaning the types of data that you are storing is super varied, it's all over the place, it's not homogeneous at all, then again, NoSQL is probably the way to go. Data is so diverse. There's dense data and sparse data. There's data that's connected and disconnected, data that is structured, semi-structured, irregularly structured. I mean, with the amount of data that we are capturing now from all kinds of different devices, from all kinds of different sources. There are just so many different ways that the data can come in. And for that, we have 4 data models that I spoke about earlier, which again have adopted their own strategy to deal with how to handle this variety of data that we see. And I know that there are databases that can accommodate, say, JSON, for example, but they're kind of always built as an afterthought. So, meaning, yes, you can store JSON in there in a relational database, but you're not going to get the native capabilities that you would in NoSQL databases. So, for example, in MongoDB, you can do embedded searches within embedded documents, or you can have automatic indexes on nested fields. And that would be something that's very difficult to do and certainly not native in some sort of add-on or a database that does offer the storage of JSON. And so for that, if your data is all over the place, it's, again, one thing to consider that NoSQL is probably the way to go. And finally, data valence. So that's here I have it as connections that exist within your data. It's the ratio of connections that exist within your data compared to the total number of possible connections. So when I first researched this and was learning about this, I'm like, that doesn't make any sense to me. So I hopefully these things will help. So fun fact, Latin root of valence is the same as value or valere, which means to be strong, to be powerful, influential, or healthy. Now, when I think about this in different spaces, I think it starts to make more sense. In chemistry, valence is the combining power of an element. In psychology, valence means the intrinsic attractiveness of an object. And in linguistics, it's the number of elements that a word combines. So keeping those kind of parallel definitions of it in the context of data, valence is the tendency of the individual data to connect, as well as the overall connectedness of the data set itself. And if that still doesn't make sense, because I know it took me a while, the explain like I'm 5 version is the higher the valence on your data set, the more connections there are within your data. That's as simple as I could put it. If you have a better one, Slack me. So keeping that in mind, knowing, hopefully understanding what valence means, over time, the data that we collect, especially if we are a data heavy company, it can become very, very dense. We collect a lot of data over time, and it can become very, very complex. And when we continue to aggregate all this data and run all of these analytics on it, it can become way more unevenly connected, meaning the relationships between them can kind of be like 5% connected, but then this one could be 25% connected. And then maybe some data from 5 years ago is somehow connected to data you're going to collect in the future. These kinds of connections, these kinds of relationships, they become much, much harder to analyze and moreover break down, especially if you are using analytics tools that for the most part have been built on top of the relational data model. So for scenarios like this, NoSQL databases may probably come to the rescue for you, specifically graph databases, because they are way more expressive in showing you the connections and relationships of your data, especially if they are this complex and this irregular. So, is NoSQL the way to go? Again, if you are on that top spectrum there, if you have large data volume, if you have a high velocity of data, meaning that you have a lot of writes, the data points that you're storing changes often, as well as your schema, your data model changes often. Maybe you're adding fields left and right, taking them out. If that's high, if you have a wide variety of data, of volatility, a high volatility of data, meaning your data is all over the place, it's varied, it's not as uniform as you would expect it to be. And if your data valence is high, meaning you have a lot of connections that may not be as easily modeled in a relational database, then Yes, yes, NoSQL is probably the way to go. It's a general rough rule. There are, of course, exceptions, but in essence, yes, you can be confident that that is the way to go. However, if you're on the opposite side, if your volume is not that large, if you're not, having to deal with web scale, if your velocity of data is pretty consistent or predictable, you don't need to, you know that it's not going to change often. If the data that you have is more uniform, it's more homogeneous, it's you know what kind of data you're going to be getting, and if the connections that you have can be expressed just fine with the relational databases, then sorry to say, but it's probably not the way to go. You probably are going to be better off just sticking with a relational database. So, yes, the title of my talk may have been like, I work for MongoDB and I'm going to sell you NoSQL, but that's not the case. I want to just show you at least a framework, a guideline, some steps that you can hopefully take with yourself and your team when you're brainstorming to kind of get these kinds of questions answered to see if it's really right for you. So great. Now we know is NoSQL the way to go based on these 4 characteristics. So step 1, check. Let's say that we find ourselves on the higher end of those characteristics. So we move on to the next step. And I like to call that acid or base. And again, I want to make very clear, these are not one-to-one comparisons. I like to think of them as the set of properties that I think the system requires. And so when we're thinking about these, the questions that I think are the most important when deciding among these 2 models is these 4 values here. So if you know that you need safe writes, if you know that those need to be prioritized over fast writes, if you know you have money to spend on high-end hardware or know that you're going to be scaling vertically, and if you know that you need a pessimistic model, a rigid model, because of the write safety that you need, then okay, fine. We'll go with relational databases because, again, the fact of the matter is it's probably going to be the best bet for you. They have been built with these properties in mind, and they have just been working that way for a while. So if these are the kinds of guarantees that you require in your system, then yes, we're going to go to relational databases. It is worth noting, though, just a little side note, that there are some NoSQL databases that do offer ACID guarantees to an extent. So for example, Neo4j, the graph database, does offer ACID compliance in their graph databases. Same with MongoDB, at least via version 4.0 and higher. We do have multi-document ACID guarantees. Now, if you're thinking, okay, well, the system doesn't need to be that rigid. What we're building here doesn't really need that. What we need to focus on is fast writes. We need to prioritize how much we can write and how much we can get stored in our database. The safety of it is not as important. It doesn't mean we're going to neglect it. It doesn't mean we're not going to have it at all. It just means it's not a priority. And if we know that this model that we require can be more optimistic, if we know that it can be more loose than the more rigid acid properties that we have seen, then base is probably the set of guidelines that you want to look for when you are choosing whether or not to go with a NoSQL technology or NoSQL database. And for that reason, because most NoSQL databases do fulfill these properties, these base properties, then that's another reason to say, yes, you have passed step 2. You fall within those lines, and you can probably move ahead and keep going towards some kind of NoSQL tech. So we have gotten through NoSQL databases. We know that if we have high data volume, if we have high data variety, our valence is high, and we have a high velocity of data that has checked, we get to the next point. If we know that the models that we need, the properties that we need fall more in line with the base properties, they're a little bit more loose, a little bit more optimistic, we can finally now get to the third step, which is where I think a lot of us tend to start, and that is the CAP filter. So this is where I think a lot of us start. We just go, what are we using? And we don't really think of anything else. And I think that's completely turned around. We shouldn't start with the tech. We shouldn't say, oh, we're going to use that immediately because I read some tweet somewhere that it's amazing and it's going to be great. I don't think we should start that way. I think that if we have gone through the first two steps of asking ourselves, of really truly understanding what our system requires, by the time you get to this step, then it should almost be very, very quick. Because if you know that you need a partition tolerant consistent system, for example, then you can start to narrow down the available systems that fulfill that. And then once you have that, you can narrow down even further via the data model that you find will be the most useful for you. So for example, if we've gotten to this point, it's almost like a funnel or a sieve that has said, okay, move this out of the way, move this out of the way. And we're now, at step 3, and we have answered all those questions. We know that we need at the very end a partition tolerant consistent system. Now the only thing left to do is decide what data model to use. So if you need a document database, hey, MongoDB. I think it's a great choice and maybe a little bit biased, but that's something that is, I think, a little bit easier to go through versus starting with MongoDB, then researching everything else, and then finding out, oh, this doesn't have something that we need or some other characteristic. Or let's say you needed some kind of key value store, then you would go to Redis. And same thing with the other different data models. At this point, it should be much easier for you to decide which one to go with, because you'll have your little checklist of things that you need from the previous two steps, and you'll know that you can kind of have a framework and check against those things when you are eventually researching the tech that you need. Now, on the other hand, if you need a partition tolerant available system and you need a wide column store, Cassandra is your best bet. Or you can start looking at CouchDB, at Amazon DynamoDB, React. Again, it's the same thing, where if you've gotten to this point, the last thing to do is see which data model fits for you and then find the database that matches that. So at the end of this 3-step guide, what I have hopefully shown here is that it's not necessarily a foolproof way to say this is the right tech that we're going to use. Not at all. This is more of a framework, almost an exercise for your team to be able to say, do we know the answers to these questions? Do we know what we truly need? And do we know that we're not going to be biased or swayed any one way because of superfluous reasons? If we can answer the questions in step 1, which is our data volume high, velocity high, valence high, variety high, then you can be a little bit more confident that whatever NoSQL database you end up choosing, it's going to work for you. Same thing, you kind of just filter it down even further. If you go through the acid and base exercise and see which properties that you need, again, you're just more solid and you're more confident in your decision because you are aware of the properties that your system will need. And finally, by the time you get to the CAP filter, which should remain at step 3, I wholeheartedly believe, it should be much easier to just focus then on the data model that you need. So with all of that said, I'm not necessarily hoping I've changed your mind specifically and said, yes, NoSQL databases, but I'm hoping that this has shown you a smarter way to consider if NoSQL databases is right for you. And in the end, naturally, you'll say yes. And that is say yes to NoSQL databases. So that is it for me. Thank you, salamat. That is thank you in Tagalog. And that is it for me. I'll be checking out the Slack. If you have any questions, we'll post the link to my slides there. Thank you for your time, and I hope you enjoy the rest of the last day of NDC Sydney.